So yes, I'm Ryan from Sandia, and I'll be talking to you today about magnetized liner inertial fusion and some spin-off technologies that came from this work that have to do with dynamic materials properties. And these are all on the Z Pulse Power Accelerator at Sandia. So as with a lot of the large facilities at the National Laboratories, this is big science, and there's lots of people involved, and this is just a rough cut of some of the people I've worked with recently and some of the institutions represented. From Sandia to Cornell to Lawrence Livermore, General Atomics, and Raytheon. There's many more that we have collaborations with at the Z machine, but this is just my subset. So Matt Gomez, I believe, showed you the awesome arcs and sparks picture of Z. This is what it looks like when it's not spewing lightning bolts everywhere. Basically, what it gives us is a megajoule class target physics platform, which is the pulse power accelerator itself. And then additionally, we've got a terawatt class laser, the Z beamlet laser, ZBL, that comes in on a beam tube from a separate building. It's coupled to the experiment. And as Matt was saying, the big game here with pulse power is to store energy over a long time period in the perimeter here and then discharge it rapidly, that same energy, so that you get pulse compression and power amplification. So what can we do with this power amplification? Well, in the Z machine, it basically comes in the form of a large fast-rising current pulse or a large fast-rising magnetic pressure. So basically, we can couple that to the axis of symmetry, which is given by the center line here, and then we can just take a metal cavity in a cylindrical geometry, right? And we can apply a voltage to it, and this cavity, due to its geometry, has some inductance associated with it. So from freshman physics, we know that the rate of rise of the current is going to be proportional to the voltage we apply divided by the inductance. And then associated with that current is a magnetic field that's going to fall off. It's going to be proportional to the current, and it's going to fall off as 1 over R. So the magnetic field is decreasing with R. And then there's a magnetic field pressure associated with that, which is B squared. And so since B goes as 1 over R, the pressure goes as 1 over R squared. So basically, we want to be as close to this axis as possible to access high pressure regimes. So that's kind of represented here, where we've got really high pressure on axis, and it's pressing out everywhere on this metal cavity. So what can we do with it? Well, here we can have an exploding geometry where we can put like samples for, say, dynamic materials experiments, and we can put probes on the outside and measure the material response. We can also go to putting samples or objects of interest in the center in a cylindrical fashion, and that's an imploding geometry, and that's going to allow us to access the highest pressures. So, moreover, if we take that cylindrical object on axis and we apply a current pulse to it and we keep it fixed at its radius, then the pressure goes as the current squared. So if we fix that radius to, say, 1 millimeter and we get a 30 megaamp drive, that's equivalent to 140 megabars, which is equivalent to a 300 electron volt radiation drive. So it's interesting that, with our compact facility, we can actually access pressure regimes such as this. To put it in perspective, I believe 300 eV is similar to the radiation drive from the NIF in a holorum. So it's exciting that we can access these regimes. Moreover, if we make this mass such that it's light enough that it can actually implode by the pressure, and then we can access even higher pressures as the outer surface goes to 0, the pressure diverges and goes to infinity. Obviously, we're not going to ever get all the current down to the axis, so we're not going to get infinite pressures, but we can access very interesting regimes nevertheless. So what can we do with these imploding systems? Well, the one thing we're most interested right now on for inertial confinement fusion is this new concept called magnetized liner inertial fusion. Actually, it's not completely new. Some of these ideas have been around, but for the timescales of the Z machine, it's kind of being looked at for the first time. So it's kind of a multi-step process. Basically, we take that cylindrical object, that can that we were talking about imploding, and we fill it with fusion fuel. And before anything happens, we're going to embed a BZ field, an axial magnetic field, and we're going to apply that over a timescale that's much earlier than the experiment so that it diffuses through all the metal, gives us a uniform axial field. And that's supplied by these BZ coils here in the cyan color. And here you can see the cavity that we talked about earlier that's going to feed in the magnetic pressure and apply it to this central object here, which is this, and it's going to implode it. So The Z machine's then next going to be turned on, and it's going to start to rise the current. And it's going to start working on this liner, trying to implode it. And just before it starts to move, we're going to hit it with the Z-beamlet laser that we talked about that couples in from another building. And that laser is going to couple to the fuel and hopefully preheat that fuel to roughly 100 to 250 electron volts. And then with the preheated fuel and the liner just starting to move, the Z machine is going to continue to work on it and drive that implosion to a high compression. And it's going to increase the fuel density and temperature, and it's also going to compress the BZ field lines, and I'll go into why that's important in a bit. But the reason why we're interested in this is because we've done some pretty sophisticated simulations, and they show that it's possible on the Z machine today that if we use DT fuel, which we're not approved to do yet, but if we use DT fuel, we should be able to obtain a fusion energy out that's equal to the energy deposited in the fuel, which would be scientific breakeven, which is to this day has still not been done in the laboratory. So Steve Slutz kind of pioneered this idea with his 2010 Physics of Plasmas paper, and then he's more recently extended this to a high gain concept in 2012 in a PRL. So I gave you kind of a schematic, and now this is kind of the timing of MagLIF. So basically it's a 100 nanosecond implosion. The Z machine is a 100 nanosecond rise time current. Here in the blue and green, you can see the outer radius of the liner and the inner radius of the liner. It's a thick liner. In red, you can see the Z machine current turning on. So as that current ramps up, the outside surface starts to move inward. It eventually compresses up, and eventually the pressure waves get to the inside surface, which sends the inside surface in, compressing the fuel. So both of them come in and eventually stagnate on axis, where the material pressure gets so high that it causes the liner to bounce off the axis, or actually at about 100 micron radius. Also what you'll see is that this is the fuel temperature right here in cyan, and you'll see there's a little blip where it turns on. That's where we turn on a laser to preheat the fuel. And so the reason why we're going to do that is because this is basically like freshman thermodynamics. You know, you have a thermodynamic state, initial state, and then you're going to do PDV work on it, and you're going to try to get to a final state. This is just adiabatic compression. So to get to the final state we need to for fusion, which is around 5 kilovolt temperatures and above, we need to start at about 200 electron volts for the compression ratios that we're talking about. So you can see the temperature rises, followed shortly by the density rising, and the pressure, which is just the product of the two, rising, and then finally the neutron production, or the fusion energy yield. So with MagLIF, we're talking about 5 kilovolt stagnation temperatures, 1 gram per cc stagnation densities, and about 5 gigabar stagnation pressures. So as I mentioned, preheat is necessary because of this initial state to final state adiabatic compression. So we typically talk in terms of convergence ratio, which is the initial radius divided by the stagnation radius of the fuel. And you can see the temperature you get to is proportional to the temperature you start at times the convergence ratio to the 4/3. So basically for MagLIF, our point design is between a convergence ratio of 20 and 30, and that gets us to the temperatures of about 5 kilovolts. So typically in ICF, like for example the NIF, faster implosions shock heat the fuel, and that's how the fuel is heated up to above kilovolt temperatures. But this is, of course, not the case for MagLIF since it's a little slower and this is an adiabatic compression. And now the other thing is you see this preheat turns on and the fuel stays hot, and then it continues to get hot instead of just cooling off back to zero. What keeps it from cooling off back to zero, because it can just conduct to a cold liner wall, is the fact that we're going to apply that BZ field that we talked about earlier, which is axial magnetization. So, and the reason why this works, or we hope will work, is because if you don't have a B field and you've got a hot region and a cold region with higher density, you basically just have collisions and there's a random walk, and eventually energy can diffuse away from the hot spot, and your density particles can diffuse away from a high density, and then there's an overall net flow that carries energy away from your hot spot to the cold conducting wall of the liner. But if you apply a magnetic field and there's no collision, say, the particle's not going to go in a linear line. It's going to orbit in its gyro orbit about the magnetic field. And then if you add collisions, which we're certainly going to need for fusion, those collisions, basically it's going to sit there and orbit on its gyro radius until it has a collision, then it's going to jump, and then it will eventually diffuse out, but it'll be much slower relative to the case without a magnetic field. So that's why we have to apply the magnetic field. But as you get to hotter temperatures, these orbits get larger, and eventually they could be so large they could hit the wall. So what's going to keep the magnetic field strong enough to keep that orbit pulled in during this implosion? And that comes from magnetic flux compression, which is where the field lines, if this is a top-down view of our imploding liner, the magnetic flux, the total number of field lines threaded through that liner, are going to be conserved as that liner implodes if it's a good conducting liner. So what that does is it actually amplifies the B field and to very high values. It basically goes as the area. So the B field you end up with is the B field you start with divided by the radius squared. So again, that diverges, and of course, because we're going to R equals 0, but well, we're going to stagnate at about 100 microns, and that results in a very high field intensity that should be able to keep the fuel hot, according to simulations. Now, to get you oriented, here's a scale size of a target. This is typically, it's about 6 millimeters tall and about 6 millimeters in diameter. And then that plugs into some larger hardware. This large pizza-sized hardware contains the liner inside, the liner target. Here's a return current structure. The cavity that we were talking about with the magnetic pressure comes in from below. Surrounding it, we've got some diagnostics to measure the magnetic field pressure. And then that pizza-sized hardware fits into the center vacuum chamber or experiment chamber of the Z machine. And then again, we've got the laser coupled in from another building. So stepping back from the accelerator scale size to the facility scale size at Sandia, here's the Z accelerator perimeter here. And here's the laser beamlet line coming in from actually all the way over in another building where the Z beamlet's generated. It goes through this intermediate building where we can do separate laser-only experiments with some target chambers. And then we can couple it all the way to the pulse power accelerator as well. Interestingly, this laser was developed as a prototype for the NIF. And when they were done testing with it, they actually shipped it over to us at Sandia, and we're very grateful to have it. So I also want to just give you a picture of what MagLIF looks like as it implodes. So we've done some fully integrated simulations now using both LASNIX and Hydra. Here's that cavity we talked about before. We're going to apply a voltage, which is going to drive a current and associated magnetic pressure. It's going to drive this liner to the axis, heating up this fuel. And at the same time, or as the liner starts moving, we're going to send in the laser to heat up the fuel to the preheat condition we want. So if we watch this movie here from a Hydra simulation, again, here's the DT fuel, here's the liner wall. If we apply the Z machine, you can see the liner starts to implode. We turn on the laser. The heating is starting to propagate through the fuel. It propagates further, heating the whole fuel. The liner continues to implode by the Z machine, squishing the fuel and getting it up to extreme conditions where we hopefully will be seeing some good neutron yields. So there's broad interest throughout the community in magnetized fuel for several inertial confinement fusion schemes. One is at Los Alamos in the Air Force Research Lab using a field reverse configuration and the Shiva star generator. There's some other work being done with heavy ion beams at the Max Planck Institute. University of Rochester has recently looked at laser-driven experiments with magnetic fields embedded. And then, of course, at Sandia, we've got the MagLIF concept. So there's been this excitement, but one of the things we were worried about with MagLIF was that it didn't really scale to some high gain condition that would possibly a future accelerator. And that was because some of the literature talked about, because you've got that axial field, you can't actually have some radial propagating burn into a high-density fuel. Well, Steve Slutz took a look at it and actually found out that that literature wasn't quite correct, and there's a way to do it, and he published that in this physical review letter in 2012 and showed that there is a high-gain path for MagLIF. Of course, this is for a future machine. So the Z machine, this is a plot of current on the bottom axis here. Z machine's in the 20 to 30 megaamp range, so this is all looking at future machines. But the extended MagLIF, or the high-gain MagLIF, is basically the same exact concept, only we're going to put this high-density fuel layer, cryogenic fuel layer, just on the inside surface of the metal liner. And that can either be a wicked foam with liquid deuterium-tritium or a frozen solid DT ice layer. But basically, what happens is the fusion reactions start in here, and then they send their energy outward, and then you can access that huge fuel reserve that you have by that high-density layer. And what happens is that you see after you get to about a generator of about 60 megaamps, the gain has this jump, and this is a log plot, and has this jump to over 100 times gain and possibly up to 1,000 times gain. So this would be really interesting for stewardship science applications, as well as possible fusion energy schemes. And for fusion energy, you're going to need a gain per implosion of at least 50, because when you consider the whole system, which is the electric production efficiency and the fraction of power recycled and the driver efficiency, all that has to be much greater than 1. So you're going to need a gain much greater than 50. So that's what this has got us pretty excited lately. But this, again, will be for a future accelerator. So the potentials of MagLIF are that the fuel magnetization allows a slow implosion relative to, say, a fast NIF capsule. And this greatly reduces the cost, as pulse power is much cheaper than lasers. Simulations indicate that MagLIF could produce significant fusion yield on Z today. So that's an interesting platform. But also that there's a high gain MagLIF concept for a possible future accelerator. MagLIF also today, on the Z machine today, will provide a platform where we can evaluate the physics that are important to this concept, or any magnetized inertial fusion concept. So it will be an interesting physics test bed to look at many physics issues. Experimental campaigns are now investigating these important issues to hopefully bring MagLIF to reality. So Sandia is planning to address these science and engineering key research questions in the next 3 to 5 years, which we can basically subdivide into liner implosion dynamics, fuel preheating, the impact of fuel magnetization, and fuel assembly and stagnation. And for several of these, MagLIF is going to require new capabilities, new engineering infrastructure to test these things. And that's what we're kind of working on now. But starting with liner dynamics, the reason why we need to study liner dynamics is because I've been talking to you about these perfect cylinders imploding in perfect cylindrical geometry. But in reality, there's instabilities, and that can make this non-cylindrical. And so we need to evaluate if that's going to kill the concept or not. So, you know, you can see that in these simulations where it starts off as a nice cylindrical slab, and that implodes, and it develops into these bubbles and spike structures, which are the magneto-Rayleigh-Taylor instability. So if you look at simulations that show 1D simulations versus 2D simulations, there's this thing called the aspect ratio, which is the outer radius of the liner divided by the thickness of the liner. If you make that liner thinner and thinner, it can accelerate to higher and higher velocities, and you get higher, more and more fusion yield. But in reality, this magneto-Rayleigh-Taylor instability rips the liner to shreds if it gets too thin. So you get this roll-off in 2D. So if you go to too thin of a liner, the yield degrades. If you go to too thick of a liner, it becomes a slow-moving slug, and nothing happens. So there's this kind of optimum in the 6 to 8 region. So we're kind of focusing on that. So we've actually done a lot of work on liner dynamics because it didn't require any new infrastructure. So we just began looking at these instabilities with just liner implosions with no fuel. This was driven a lot by a 3-year LDRD. Also, Dan Snars has won a presidential early career award, and so we'll continue to look at this. And we've, since 2010, been publishing several physics of plasmas and some PRLs on these experiments. The bottom line is that the original MagLIF calculations were consistent with the data that we've obtained to date. So the first experiments that we did were to just code validation exercise to see if our codes were getting the magneto-Rayleigh-Taylor instability correct. So we put in controlled machined perturbations, and we wanted to watch this evolve, the magneto-Rayleigh-Taylor instability evolve. And the way we watch it evolve is through radiography. And so for these, there was no fuel, so there's no laser preheating or anything. So we used the laser to do radiography. So the laser comes in off-axis, hits some manganese targets, which produce X-rays that get projected through the load, through the imploding liner here, collected by some crystal optics. So through the load to some crystal optics. Those then select a particular wavelengths to reflect and image through some limiting apertures and onto a detector. And that selects 6.151 keV photons for the imaging, for the radiography. So here's an example radiograph, pre-shot radiograph, where you can see the perturbations that were imposed. And this is aluminum liner, so it's just a black silhouette because we can't see through it with 6 kilovolt photons. And the current is, of course, applied to the outside, and there's going to be a pressure to drive this implosion. And if we focus on these edges and watch them evolve in time, you'll see these small perturbations start to grow into large bubble and spike-like features. And so it's a well-prescribed experiment that's good for a 2D code to test. So these experiments were written up by Dan Sonars in a physical review letter in 2010 and Physics of Plasmas in 2011. And if we look closely at some of the data, one of the predictions actually of the LASNIX code was that we'd see these little ablation streams jetting from the bubble regions in between the spikes. So these are basically ablation jets. And then we, sure enough, saw them in the experiments, which was actually a pleasant surprise. And then we also did some, if we looked at the overall growth amplitude as a function of time, we saw that the experiment was in very good agreement with the simulation as well as analytic theory. But looking at silhouettes has its limitations, so we decided we would like to look at some beryllium liners, which are also a candidate for MagLIF. And the beryllium opacity is low enough that 6 kilovolts will penetrate, and so we can actually get full images of the total imploding volume. Now this beryllium liner here did not have machined perturbations. This structure grew from just the surface finish. So, and it grew in an amazingly correlated way. You see these dark bands going all the way across, perfectly horizontally, correlated from left to right. And so this is something we're currently trying to understand. So we followed these beryllium liners all the way to stagnation and to see how they would do for MagLIF. So basically, here's the current pulses from all the repeated experiments. Here's the liner trajectory in time. And these vertical bars represent the times we took the pictures right before, hopefully, fusion would start in a non-surrogate case. If we look at these like a movie, like we did the simulation, we can follow the implosion in through stagnation, and then it starts to kink up due to the kink instability. So taking these data, we wanted to then see how our codes would do reproducing them. So we took these radiographs experimentally, then we generated some synthetic radiographs with various codes. We found that to get agreement was not trivial. It depended on the initial conditions. In LASNIX, or in Gorgon, in 3D codes, we found that we had to have some initial azimuthal seating to get the azimuthally correlated structure that we see in the experiments. And so that's a question we want to address. In the case of LASNIX, it's 2D already, so everything's perfectly correlated azimuthally. But we found that if we included too fine of a scale size, then the MRT actually overgrew in the simulation. So we actually had to cut off the wavelength of the pre-imposed structure to 200 microns. It turns out that this was actually the way LASNIX was run for the original MagLIF calculations, and that was just a fortuitous accident. But it turns out that the simulations that said MagLIF would be interesting were run in this fashion, which agree with the experiment. So that's good news for MagLIF. But why do we have to have this azimuthally seated perturbation in the 3D Gorgon simulations? Well, if we look at the surface finish of our liners, it turns out they're not perfectly smooth, although they're very, very well machined down to 50 nanometers for beryllium. They have fine azimuthally correlated scratches on them from the lathe that they're manufactured on. So we're interested actually to see if we can affect that correlated structure by changing that azimuthally correlated or horizontal structure to vertical structure, an axially correlated structure. So we're doing that through polishing, and we're going to be testing that shortly. We've actually done some tests, but they were a little inconclusive, so we're going to follow up with that some more. Let's see how we're doing on time. Okay, so another new recent development is that it was a little hard to assess the inside surface and how stable that is in those previous radiographs I showed you. And that's because you're looking through the outside, all that structure on the outside, you have to look through that to see the inside surface. So, and that leads to confusing interpretations. So Dmitry Ryotov came along and said, hey, you've got this low opacity beryllium, why don't you put a high opacity thin aluminum foil on the inside, and that'll give you a high contrast marker for where the inside surface is. Now, I should have said earlier that the magneto-Rayleigh-Taylor instability works, builds up on the outside surface and works its way inward to the inside surface. That's why we want to start off with a thick enough liner that the whole implosion is complete before the MRT works its way all the way through to the inside surface. So that's the point of that aspect ratio plot. But So anyway, we put this high opacity aluminum on the inside surface, and you can see the MRT starting to build up here, but the wall looks very straight. And these other objects on the inside were diagnostics to measure magnetic field and some other things I'm not going to go into. But we also took one very high convergence radiograph with this aluminum layer, and this is an on-axis rod just to suppress some X-rays from being produced by the liner. But it turns out that this radius of this rod is about 100 microns, and that is the stagnation radius for MagLIF, so that's our target convergence ratio. And we're only about 500 microns away from it in this case of this image. And there is some wiggle to the inside surface, but it's very minor. In fact, the original MagLIF calculations from the 2010 paper said there would be some wave in the inside surface, but not too much. The bubble hasn't broken all the way through the liner, and if it breaks all the way through, you lose your inertial confinement. So you have to have some liner material left. And you can see here behind even the most dominant bubbles, there's plenty of liner material left. It doesn't look to be in danger of breaking through the liner wall. So that's good news for MagLIF. Even better news is some recent developments that Kyle Peterson has been looking at the electrothermal instability, which we think could be actually seeding there's two different theories. It could be the initial surface finish from the lathe, or it could also be this electrothermal instability. The electrothermal instability develops from very fine structure and it quickly saturates, but that saturation could then seed the magneto-Rayleigh-Taylor that we observed later in the experiments. So the thought is that if you can delay the electrothermal instability or mitigate it, then you could delay the onset of magneto-Rayleigh-Taylor instability. So what Kyle found through simulations was that if you put this dielectric coating, actually a dielectric, on the outside of this conducting liner, it would tamp the growth of the electrothermal instability. So here's a case with no coating. You can see this instability structure growing very significantly. And then with a dielectric applied, it's tamped severely. So we did an experiment, and half the liner, so this is the right edge of the liner, and this is the left edge of the liner. We cut out all the stuff in the middle. It's the same shot, same current going through it. And you can see the magneto-Rayleigh-Taylor starting to develop quite significantly on the right edge, and it's very much mitigated on the left edge. So that's a very interesting result, and we're going to be following up on this. Kyle Peterson is going to be preparing a manuscript for this. Another thing we can look at for MagLIF is the different states that we can put the liner into as we drive the implosion. If everything I've talked about so far is used the Z machine in short pulse mode, which is this fast rising pulse of 0 to 20 megaamps in 100 nanoseconds. If we do that, the result is that the liner gets shock compressed. This is not the fuel, this is just the liner. So the liner itself gets shock compressed. The inside surface sits still until the liner. So if you look at just a 1D mass profile, you see that there's this shock wave propagating through in time. So this first frame, second frame, third, and fourth. But the inside surface sits still and at its initial density until the shock wave gets there, and then it breaks out and the whole thing starts moving. But you can tailor the current pulse shape on Z, and you can ease it on, and that'll give you a quasi-isentropic compression or a shockless compression. And that'll keep the liner, there's several benefits possibly for MagLIF. You can perhaps get higher areal density because the liner is more compressible if you don't shock heat it. You're not wasting energy in shock heating. But anyway, you basically send these gentle pressure waves through and you ramp it up slowly, and then the whole thing starts moving together as a unit. But one of the reasons we were looking at these A and B cases was actually for dynamic materials as well, in a collaboration. So dynamic materials is interested in measuring shock hugonios and isentropic or isentropes to higher pressures than they're currently able to. And earlier we showed that exploding geometry that they typically use. Well, this is a converging geometry, so you can access higher drive pressures. In this case, you would make beryllium your material sample. So we've done some shock experiments. We've also done some isentropic experiments. And from the isentropic experiments, there's this unfolding procedure that Matt Martin wrote up in Physics of Plasmas in 2012, where we were able to take the radiographs, process them through some hydro equations. Well, we convert the radiographs to mass images, and then we run them through some hydro equations, and we were able to unfold the isentrope. And we were able to, and this is experimental, and it actually extended the measured isentrope of beryllium out to 5.5 megabars and 5 grams per cc, which is the highest that it's ever been done experimentally. Previously, it was around 2 megabars in the exploding geometries. So that was a nice breakthrough. Moreover, we could do this with shocks as well, presumably, but we haven't gotten there yet. So aside from liner dynamics, we've also got fuel preheating. And I showed this image earlier of the facility with the Z-beamlet laser coupled to the facility where we're going to use that to preheat the fuel. Currently, the Z-beamlet laser can deliver about 2 kilojoules to the fuel. And then we have to worry about how much is actually coupling to the fuel. For MagLIF, it would be really better if we had about 6 kilojoules, but there's some straightforward upgrades that we can do, engineering upgrades, that we're going to be actually starting to implement in the next couple of years. But again, there's this question of, despite how much laser energy we have, how much is going to actually couple to the fuel? So we've got some, we've been looking at some of the research people have done at other facilities. They found agreement between what Hydra says and what's actually coupled to the fuel. So, but we still believe we need, need to investigate this on Z as well. So we've got some Hydra predictions, and we're going to start testing that shortly, actually. There's also issues, more engineering-related issues, concerns about debris. In order to preheat the fuel down the axis, you got to bring the beam in and shine it right down into the target on axis. But with a Z pinch, you tend to have jets going axially out the top and out the bottoms. So there could be high energy debris coming back up towards the optics. So these are things we're going to be testing actually next month. And then there's also the impact of fuel magnetization. We've developed the coils. We've actually fielded them on their first shots already. I'll show you some of that in a minute. But basically, it's just a Helmholtz coil pair, and the goal is to have this, the experiment's on a 100 nanosecond time scale, and this rise time here is about 3.5 milliseconds, so it's much longer. It allows the B field to diffuse through all the metal uniformly, and it needs to apply that B field uniformly throughout the fuel to less than 1%. That was our engineering target goal. And then the reason for the split Helmholtz pair is so that we have diagnostic access. You can actually see the liner inside, so some of our diagnostics can image the implosions. We can put those coils together to access higher magnetic fields, but right now we've got a point design for the split version that's about 10 Tesla. And eventually we want to extend that to 30 Tesla, which we can do by putting the coils together. There was also a bunch of infrastructure that was needed for these coils. The first was a test facility that's actually in a different building, and this is where we test all the coils before they head over to Z. We also had to put in some new capacitor banks to drive the coils over at the Z facility. This here is the tank wall that holds all the Marx generators that store all the pulse power energy. And then we've got these capacitors to drive those coils as an auxiliary system. And it's 900 kilojoules in these capacitor banks, and that's, we believe, is enough to meet our long-term goals of 30 Tesla. So we actually already commissioned these. They're working. We've got some experiments. This just gives you an impression of the energy involved with pulse power on Z. This is the pre-shot image or photo of nice, beautiful, shiny hardware with the magnetic field coils. And this is the post-shot, obviously, and it's gone. There's nothing left. This is actually one of our most destructive shots we've seen in a while. Something to do with the magnetic field that we're not quite sure about. You see all this debris here. This is actually, I can't remember the name of the material, but it has to do with the conductors that are wound in the coils. It's some insulator material. It's just been blown all over the chamber. It was quite a mess, and there was really nothing left. There was almost nothing identifiable. So it's equivalent to a few sticks of dynamite. So that gives you the impression, I think. But and then most interestingly were these great radiographs we got from these first experiments using 7 or 10 Tesla as our seed field. So these are flux compressing experiments. We don't have a diagnostic yet to measure the flux compression, but we are assuming that it's working fairly well. But here you can see a radiograph of the exact same target without the BZ field applied. And it's that horizontal structure that we saw earlier, that ring-like azimuthally correlated structure. We applied the BZ field, and instead of ring-like structure, you get this helical structure. It's actually, you get this crosshatch pattern because you're seeing through the front and back side of the liner. So you're seeing the positive and negative slopes, but it's actually multiple helices intertwined. And that's very interesting because the magnetic field, the B theta field from the Z machine is actually quite a bit greater than 10 Tesla very early in time. So and this is very late in time. And to get this severe, like 45-degree angle, that means something must be getting imprinted very early in the implosion, which is still somewhat of a mystery. And to date, there is no simulation that's getting this correct, 3D or otherwise. So this is very interesting. And Tom Awe will be writing up a manuscript on this, hopefully getting that out shortly. So also, I guess I'll point out that there's these white blobs in the non-BZ case, and those white blobs are from time-integrated self-emission. They're from places where the instability pinched down very hard and created emission. And actually, it was significantly reduced in these, which we think could be an indication of stability being greater stability because of the magnetic field. But there's more work to be done there. So finally, fuel assembly and stagnation. Well, since we haven't even attempted to produce any neutrons yet with MagLIF, we haven't really done any work specifically for MagLIF, but we're going to be leveraging work we've done elsewhere. We've had some collaborations with NIF. We've got some diagnostics built from our wire array Z-pinch days where we were doing indirect drive spherical capsule implosions using the radiation from wire array Z-pinches. So we've got neutron diagnostics available, and we'll be ready to measure hopefully some healthy neutron yields. So our timeline is looking like this. Hopefully in the next 3 years, we should be able to say whether MagLIF is promising or not. Magnetic field coil capability was actually, this is an old slide, was commissioned in, I think, February. Laser preheating, we've done some initial standalone tests, but we'll also be following up in July. First integrated MagLIF experiments will hopefully be in August. Of course, these will be at significantly reduced parameters relative to the full MagLIF concept. So this will be reduced power MagLIF, say. We want 30 Tesla, we got 10. We want 6 kilojoules, we've got 2. We want 25 megamps, we've got 16 to 18 right now for the particular loads we're driving. And we want DT fuel, and right now we've got deuterium only. So, but it should be interesting to see what we get using that. We're kind of on a cliff. If we can get the laser energy up, we should be able to get really healthy yields, but we can start investigating physics with this platform immediately. We're already working on the improvements needed to achieve these higher conditions that we need for MagLIF. And magnetic fields and pulse power is kind of ubiquitous in nature and around the world today. Russia is saying that they want to build a 50 megamp, 150 nanosecond pulse power machine. China has recently built a pulse power machine, and I guess I've heard that they're working around the clock 4 shifts. University of Rochester has also been looking at magnetizing some implosions on the Rochester laser as well. But hopefully, and then of course MagLIF. So that's it. Any questions?